Hi, so now we're looking at section 2.6, which is called subspaces. And you may be wondering, what in the heck is that? Subspaces? Okay, so this is a good time to open up section 2.6 in the notes and to have MATLAB open and ready to do some calculations, and that'll be good practice. So pause the video now if you'd like and get your setup ready to go. Okay, so there are three subspaces that we care about: the null space, the column space, and the row space. And what is the null space? Okay, well, we find the null space by solving the homogeneous equations, right? We find the vector x such that the matrix A times x equals 0. All right. And then we write the basic variables in terms of the free variables and put the solution in vector form. Okay, so we get the solution to the homogeneous equations in vector form, and that will produce a set of vectors that span the null space. Okay. Um, and in vector form, we often use scalars times the vectors, and so that linear combination will actually produce the span of the null space. It'll produce all possible vectors that are in the null space. All right. And we'll also talk about the column space, but let's do some null space examples first. Let's check over here in the textbook. Okay, and this is example one. Again, I'm going along with the subspaces section in the online notes, and I'm doing this exact matrix A. And I actually copied using the upper right-hand corner here for matrix A. That's how I got this stuff in. Notice that I'm augmenting the matrix capital A. After I create it in this step, I'm augmenting it in the second step here with the zeros vector, right? It's the zeros is a matrix full of zeros, but I've specified 3, 1, so it's a column vector with 3 elements. And I'm also all in one go, I'm producing the row reduced version, the RREF form of A. And notice, because I have semicolons at the end of these first two commands, they won't generate any output. If I take the semicolon off, you'll see that I will get, it shows the augmented matrix, and then it shows the row reduced form of the augmented matrix. And you can verify that that augmented matrix is in fact the one that we were wanting. And what do we find out? Well, we find out that 1 times x sub 1, right? 1 times x sub 1 minus 3/4 of x sub 3 equals 0, right? Here's where the augmentation line is, so that's basically where the equal sign is. And then we take the top row and we see that x sub 1 equals x sub 3 times 3/4. Why? Well, we have to subtract the 3/4 x sub 3 over, and that's why the minus sign becomes positive. That's also why in row 2, right, we have a negative, right, because it's positive x sub 3. So x sub 2 equals x sub 3. But again, when we move the x sub 3 over, we get the negative x sub 3. Okay, so what's going on here? Well, let's get rid of the ink and scroll up just a bit. Okay, so we're going to take these equations for x1 and x2, and we're going to turn them into vector form. Okay, so when we go from these equations, right, we know that x sub 2 should equal negative x sub 3. All right, that's why the negative is here. Sorry, the negative is here in the second component. Why? Because x sub 2 should be equal to negative x sub 3. And remember, we're replacing x sub 3 with t. All right, so it's a scalar value, right, or real number in this case, right? And then the top row says that 3/4 times x sub 3, right, which is right here, 3/4 times t, and that should be what x sub 1 is equal to. What's x sub 3 equal to? Well, again, x sub 3 is the scalar t that we've pulled out, so x sub 3 is just equal to 1. Okay, so what does that all say to us? It says that the null space is the set of all vectors such that I can put in any real number t that I want to. So there are infinitely many solutions, and they're of this form. They have to be some scalar product of this vector. All right? Have to be a scalar product of this vector. So all I have to do is solve the homogeneous equations, put the solution in vector form, and then I'll have the null space. Let's try that again. Example 2, again, going with the online notes, and I've pretty much copy pasted from there. Notice that I'm doing the REF and adding the augmented zeros matrix all in one go here. And when I execute that, x sub 1 equals 0, x sub 2 equals 0, and x sub 3 equals 0. That's what I get, right? Because the augmentation line would go right here. So the 0 vector is the solution to the homogeneous equations. That's the only one we've found. So the whole null space is just the 0 vector, okay? So there's just one vector in the null space, and it's the 0 vector. Now, okay, that's fair. The null space does consist of just this one vector, and that's what happens when we get what we were looking at in the last section. We would have called this the trivial solution. So it turns out that the solution space is a little trivial. We don't call it that because it's just this singular vector, this single vector, which is the 0 vector. All right, so that's what happens when we get everything equaling 0. And then example 3. Okay, so notice this is matrix C is a 3 by 4 matrix, and when we add the zeros to it, right, we end up with a larger matrix. Let me take this semicolon off so you can see. So this is the matrix C. All right, and then when we add the 0 matrix to it, right, there's actually, right, what we want we want to add a column which is a 0 vector, right? And you see that coming in, but there are solutions happening here. Get rid of the ink. Okay. And what do we see? Well, so now if this is the augmentation bar, we have that x sub 1 equals 27 times x sub 4. And let's go, we're going in reverse order here, right? So x sub 3 equals, x sub 3 plus negative 2x sub 4 equals 0. So I add 2x sub 4 to both sides. So I find out that x sub 3 equals 2x sub 4. Same thing, I find out that x sub 2 plus 9x sub 3 equals 0. So when I subtract, I get minus 9. I also am going to get a minus 27 when I subtract that. So getting rid of the ink for just a second and scrolling up so we can see it. Sorry, let me let me run this. Let me get over here. Sorry, there you can see the solutions that we find, and we're going to put them in vector form. So we can see the vector form, right? This is how we write solutions in vector form. And remember that we were solving the homogeneous equations, right? And so we find this vector form, there's just this one vector times a scalar t, right? So the set of all possible vectors like this, where t is some scalar, or in this case, a real number, that's going to be the null space of the matrix. The null space of the matrix A is the set of all possible vectors that look like this constant vector times t, where t can be any real number. Okay, so let's go and get rid of the ink and check out example 2. So again, example 2 is straight from the online notes. And when I run this, you notice that what happens is we find out that x sub 1 equals 0 and x sub 2 equals 0 and x sub 3 equals 0, right? This is RREF form of the augmented matrix with the zeros matrix tuned in. But what we found is, right, so if we're solving the homogeneous equations, I'm sorry, this is B. Right, so we have the matrix B times the vector X. Again, we're solving the homogeneous equation. So we're finding the vector X that's equal to, when I multiply it by B, is equal to the 0 vector. But it turns out that we found out that the solution vector is also equal to the 0 vector. So the null space is just the single vector, the 0 vector, okay? So let's get rid of the ink and try one more example of the null space. And again, this is from the online examples. And when we do matrix C and the RREF form, notice this, right? So again, the equal sign is here, but I can move this over. So I have x sub 1 equals minus 27x sub 4, right? And x sub 3 equals 2x sub 4. And x sub 2, move the 9 over, I have minus 9x sub 4. So what happens is, when I solve the homogeneous equations, I get scalar multiples of this constant vector with the three elements 2, -9, and -27. Okay, so that's how I find the null space. The null space is just solving the homogeneous equations. Matrix A times the solution vector X equals the 0 vector. And then writing all possible solutions in vector form. And that gives me the null space. All right. Well, what about the column space? Let me get rid of that ink. There we go. And again, to get to vector form, we write the basic variables in terms of the free variables. So the basic variables correspond to the pivots, right? And the free variables are the other variables, the variables that correspond to the columns that don't have pivots. And that's how we get to vector form. And once we do, we have the null space, or the group of vectors that span the null space. All right, so the column space, well, okay. The column space makes sense. It is, by definition, the span of the columns of A. But how do we find the column space? That's slightly more complicated. So the first thing we do is we row reduce A, which is great, by the way. If I'm doing homogeneous equations, excuse me, if I am doing the null space and the column space, I just have to do the RREF once, okay? Why? Well, because for the column space, all I do is I find which columns have pivots in them. And since since the pivots correspond to linearly independent columns, those are the columns in the original matrix that form the column space. The span of these linearly independent columns forms the column space. Okay. Let me get rid of the ink and jump over and do the example here, right? So they're going back to matrix A, which was example 1. And I'm just putting in the same thing, the row reduced versions of the augmented matrix, right? And notice that we're not looking at any of these solutions. We're just looking, hey, there's a pivot here, and hey, there's a pivot here. What does that mean? It means that that corresponds to two linearly independent vectors right here. And remember, this is solving the homogeneous equation. It doesn't matter exactly what we're solving. We just need to know which vectors are in, which columns of A are linearly independent, right? Which correspond to the pivots, okay? But that means I need to go to the original matrix for the first two columns, right? Why? Because I have a pivot in column 1, I have a pivot in column 2, so I go to column 1 and column 2 in the original matrix. That's important. So it turns out that row reducing changes the column space. Now, you're like, wait, I thought it wasn't supposed to change the solutions, and it doesn't. It turns out that the row space is unchanged by row reducing operations, but it can in fact change the column space. So what do? We go get these two vectors, the first two columns of A, because of the pivots, right? And then any linear combination of those two vectors is in column space. So getting rid of the ink, right? We just take these first two vectors, which correspond to the first two columns of A, and their span is equal to the column space. Well, what's their span? Well, the span is the set of all linear combinations, right? So I have S times the first vector and T times the second vector, where S and T are real numbers. Again, they're scalars. These can be complex valued matrices, so these could be complex numbers, but they're scalars, and in our case, they're real numbers. Okay, and that's all you have to do to calculate the column space. Sorry, let me get rid of the ink. So it's a fairly straightforward procedure. You have to remember, though, you have to go back to the original matrix. Okay, so I find out via row reduction where the pivots are. And then I find the corresponding columns in the original matrix that correspond to the pivots. That's how I find the column space, okay? So the key takeaways, to find the subspaces that correspond to matrix A, I just row reduce the augmented matrix, right? I solve the homogeneous system. Why? Well, because the solutions of the homogeneous system in vector form is the null space. Okay, so that's how I get the null space. And then when I row reduce, I can find out where the pivots are, right? And then that's how I find the columns in the original matrix that form the column space, or the span of which form the column space, right? And this isn't a key takeaway, but it turns out the row space is a set of linear combinations of the rows of A, which turns out to be the rows of the RREF of A, which corresponds to the pivot. So again, even though we're not talking about that in this section, that's not part of it. One of the key takeaways is as soon as I row reduce this, I can find the null space, I can find the column space, and it turns out I can also find the row space. And those are all three subspaces that correspond to the matrix A.